ॐ सहना भवतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, today we shall consider about trees and search trees. A tree is a digraph with a non-empty set of nodes such that there is exactly one node called the root of the tree, which has degree 0. Every node other than the root has in degree 1. For every node A of the tree, there is a directed path from the root to A. So, a tree has a structure something like this. There is a root which has got in degree 0, and you may have other nodes like this. This is a tree. These are called leaves. The other nodes are called internal nodes. For every node, there is a directed path from the root to the tree. The following are not trees. Consider this. If you have something like this, this is not a tree because you are having two nodes with in degree 0. So, that is not a tree. And look at this. This is also not a tree because you have a root, no doubt, but this node has in degree 2, and so this is not a tree. And similarly, if you take something like this directed in this manner, this is not a tree because there is no node with in degree 0, there is no root at all in this. So, this is not a tree. So, a tree has something, it has a structure something like this, and you may have more and more levels, you may have something. Now, for this node, these are the sons. Say if I label them as A, B, C, D, E, F, G, H, I, J, K, say, then for C, F, G, H are the sons, and for I, H is the father, for D and E, B is the father, and so on. A has 2 sons, B and C, C has 3 sons, and so on. Now, A is an ancestor of I, ancestor of I. It in the path it comes before I from the root. C is also an ancestor. I is called a descendant, and look at this portion, this is called a subtree, and the subtree has root at C. Similarly, you have a, if you take this, this is a subtree, and this subtree has a root at B. So, these are some of the terminologies associated with tree, and generally when you draw a tree, you do not draw the arcs, you just draw a tree like this. just draw like this. It is supposed to be directed in this way, and this is the root. Now, what is the height of this tree? The height of the tree is the length of the longest path, length of the longest path from the root, longest path to a leaf from the root. This is called the height of the tree. So, look at this, the height of this tree is 3, the height of this. Now, the root is supposed to be at level 0, these 3 nodes are at level 1, these 3 nodes are at level 2, these 2 are at level 3, the height is 3. So, these are some terminologies associated with the tree. Now, let us consider this. Let T be a tree with root R and A be any node of the tree. Then there is a unique directed path from R to A. You have a tree T, something like this. Then by definition there is a path, A is any node, there is a path to A from the root, but we want to show that that is unique, there is a unique path. How do we prove that? That there is a path from, directed path from root to A is clear, by definition it is there, and it is also a simple path. You can very easily see that it is a simple path, but that path is unique. How do we prove that? You can prove by induction, proof by induction. You have a tree, say some tree like this, it is only a small tree I have drawn, but generally any tree, and let Sn denote the set of nodes such that if A belongs to Sn, then the length of the path from root to A, the length of the path from root to A is less than or equal to n. Now, the basis class you can prove like this. S0 means it is only the root. For the root there is only a one path of length 0 from itself to itself. So, that is unique. If you take S1, it denotes nodes which are sons of the root, and you can very easily see that there will be only one directed path, the path is unique to them. So, that is okay. Now, induction portion, assume that the result is true up to n minus 1, that is up to Sn minus 1, that is if the node is such that the length of the path from the root to that node is less than or equal to n minus 1, then there is a unique directed path from the root to that node. Then prove for n, you have to prove for n. So, suppose A belongs to Sn, there are two possibilities. One is A belongs to Sn minus 1, that is the length of the path from the root to A is less than or equal to n minus 1. Then by the induction hypothesis the result holds. The other thing is A does not belong to Sn minus 1, that means the path from the root to A is of length n. From root the path to A is of length n, That means there is a path like this, root to some node and then to this node. This is A, some node B, this path is of length n minus 1 and from B to A you have a path. Suppose this path is not unique, there can be another path, say if there is another path, then the integrity of this will be 2, but you can have only integrity 1 for this node A. So, from this will have only integrity 1 means there is only one arc like this entering into A, and this node B will belong to Sn minus 1, that is the length of the path from the root to this node is of length n minus 1 and this path is unique. So, this path is unique. So, like that you can prove, and by induction hypothesis the result is proved. Now, arithmetic expressions you can express as trees. Let us consider some arithmetic expression and see how they can be represented as trees. Look at this tree where the internal nodes represent operators plus star, star, some 4, 5, minus 6, 2, plus 7, 5. What does this tree represent? This tree represents an arithmetic expression and you can write it like this. Four star 5 star 6 minus 2, that is this portion, and it should be added to 7 plus 5. This arithmetic expression is represented as a tree like this. Now, how do you evaluate this? Level by level you can evaluate. So, if you try to evaluate this, 4 star 5 is 20. So, this will be plus star plus, and here the evaluation gives you 20, and here 6 minus 2 gives you 4, and plus 7, 5 you have. So, this gives you, this evaluates to 20 into 4, 80, and 7 plus 5 is 12. Now, this evaluates to 80 plus 12, 92. So, the arithmetic expression evaluates to 92. This is the way in the compiler. A compiler is a large program which translates a machine language which translates a source language, a high level language into a machine code. And there are two parts of the compiler, one is the analysis part and another is the synthesis part. In the analysis part, the source program is analyzed and kept inside the computer as in an internal form. The internal form could be a triple or a quadruple or a tree or a postfix notation, some prefix notation and something like that. Let us see what is postfix notation, prefix notation a little bit later. Now, when it is represented inside the computer like this in the internal form, and then the code is generated. But essentially the evaluation is done in this manner, and for that the proper code is generated. You will learn more about it in the compiler design theory course. But the main point to note is that the arithmetic expression is can be represented as a tree like this, and the internal nodes or operators, leaves or numbers or variables, whatever it is. It could be something like A, B, and then A can be given a particular value, B can be given a particular value, and so on. Now, you will see these points very clearly. Every directed path in a tree is a simple path, because there are no node will be repeated. There are no loops on the nodes, there are no self loops in the nodes, and a tree has no directed simple cycles of non-zero length. So, if you have a tree like this, and usually we do not write the direction of the arcs explicitly, but without them we write, but suppose you also draw the arcs. Look at this, every path is a simple path, and there are no self loops, there is no directed cycle, and the other thing is the only cycle undirected simple cycles of non-zero length are of length 2. That is, between these two, suppose you have some arc like this AB, you can look at it as an undirected cycle ABA. You can look at it as an undirected cycle ABA. That is what is said by this. This is not a major point. The point is there are no cycles here, there are no self loops, and every path is a simple path. Now, when you look at a tree like this, this has 2 sons, this also has 2 sons, this has 3 sons, this has 3 sons, this is a ternary tree. A ternary tree will have each node will have 3 sons, 2 sons, 1 son or 0. It will not have more than, no node will have more than 3 sons. When you look at a binary tree, this is a binary tree, this is a binary tree. Each node will have 2 sons, 1 son or 0 sons. The leaves have 0 sons. This node has got 1 son, this has got 2 sons, this has got 2 sons, and so on. No node will have more than 2 sons. That is called a binary tree. In general, n-ary tree means each node will have n sons or less. Now, what is a complete n-ary tree? N-ary tree means each node will have I sons. I can vary from 0 to n. A complete n-ary tree means each node has 0 or n sons. So, if you take the root, it will have, say, it can have n sons, and if you take any other node, it can have n sons, otherwise it will be a leaf. This is called a complete n-ary tree. Okay. What is a complete binary tree? Complete binary tree. Each node has 0 or 2 sons. For example, look at this. This is a complete binary tree. Look at this tree. This is also a complete binary tree. Look at this. This is not a complete binary tree because this node has only one son. So, this is not a complete binary tree. It is a binary tree, but not a complete binary tree. So, binary trees are very much used for search purposes. Ternary trees are also used. Let us see how we can use binary trees as search trees. Before that, what can you say about the height of a binary tree? So, some results about the height of the binary tree. If T is a binary tree of height h and with n nodes, then n is between h plus 1 and 2 power h plus 1 minus 1. Moreover, there exist binary trees in which these bounds are attained. How do you prove that? You have a binary tree, say, let me draw a binary tree. This is a binary tree, say. How many nodes are there? 1, 2, 3, 4, 5, 6, 7, 8 nodes are there. What is the height of this tree? 3. N is 8, H is 3 here in this example. Now, in general, N is between H plus 1 and 2 power H plus 1 minus 1. In the worst, let us consider the worst case scenario, you can have a binary tree like this. A binary tree will have, if it has 2 sons like this, a node has 2 sons, this is called the left son, this is called the right son. So, you can have a tree like this where there are no right sons at all. Then what is the number of nodes here? N is 4 here and H is 3. So, N will, the worst case N can be H plus 1. This is the one. The other way around, every node has got 2 sons x, so at every level. So, you may have a tree like this, a binary tree. Sometimes this is called, this is a complete binary tree, but this is a complete binary tree with height 3. This is also a complete, please remember that this is also a complete binary tree. To distinguish between complete binary trees like this and this, sometimes this is called a full binary tree, but that is not a very common terminology. Some books use that notation. So, what is the number of nodes here? The number of nodes is 15, N is 15 and H is 3. So, what is 2 power H plus 1? 2 power H plus 1 is 16 and 2 power H plus 1 minus 1 is 15. So, in this case you get the maximum number of nodes with the, for this height. For height 3, the minimum number of nodes you can get is 4. The maximum number of nodes you can get is 2 power H plus 1 minus 1, 15 you can have. You can also get like this. If the height is h, at level 0 you have 1 node, at level 1 you have 2, at level 2 you have 2 squared nodes, at level 3 you have 2 cubed and so on. So, in general if the height is h, if the height, I will write it here, and the height is h, you will have, so maximum node you can have is like this. It is a geometric series sum, and it will sum up to 2 power h plus 1 minus 1. So, we have this result, and the next one is a binary tree with n nodes. The height is at least log n, that you can very easily see. If say for 7 nodes you can have height 2 tree. For 8 nodes the minimum will be 3. For 9 nodes the minimum has to be 3. For 15 nodes you can have a tree with height h. For 16 nodes you will have minimum height is required is 4. If you have 16 nodes, there should be something like that at one position, the height will become 4. So, we can very easily see that if there are n nodes, the minimum height of the tree will be log n, taking the floor function. Now, all these things we have seen, but how do you formally define a binary tree? How do you formally define a binary tree? Formal definition. We have seen that sets can be defined inductively. So, we can use an inductive definition to define a binary tree. So, the basis part will be the root node alone, like this, a single node is a binary tree. Now, the induction class you write like this: T1 and T2 are binary trees already constructed with roots R1 and R2 respectively. Then have a new node R, take a new node R, then R with an arc to R1 along with T1. This is a binary tree. Then R with a right arc to R2 and the tree T2. This is a binary tree. And R along with an arc to R1 and an arc to R2 with the tree T1 and with the tree T2. This is also a binary tree. So, the basis class is you take a single node, that is a binary tree with no arcs. And if you have two binary, induction class is defined like this: if you have two binary trees T1 and T2 with roots R1 and R2 respectively, take a new node R, then R along with an edge like this and T1 is a binary tree, R along with an edge like this to R2 and T2 is a binary tree, R with an edge to directed edge from R to R1 and R to R2 along with trees T1 and T2 like this is a binary tree. Of course, when you define a set inductively, you have to also use what is known as the extremal class. So, here we have to mention the extremal class. Earlier we have seen that the extremal class is the same for all, that is all binary trees can be obtained in this manner and nothing else will be obtained. So, this is the formal way of defining a binary tree. Now, these binary trees are ternary trees, they are very useful in database and they are used as search trees. Data is stored as a record will have several fields. For example, you have a record, say, it will have several fields. For example, employee. In a company, you want to store the records of all the employees. It will have employee number, name, department, whatever it is, something like that. If you take US and all, you may also have social security number, name, and so on. Now, when you want to search for some record, it is better if it is the records are stored in the form of a tree, so that the search takes less amount of time. If you have it as a linear record, one by one you have to search and it will take lot of time. Here we have seen that you can, when you have n nodes, the height can be log n. So, you can very easy, in log n time you can search, whereas if you store it as linear record, you will require search time n. Now, when you want to search, you have to search through a key, what is known as a key. The key should be unique for each record. For example, if it is a department number or something, there may be so many employees in a department, so that cannot serve as a key. Whereas, if you take the social security number of a person in, that is applicable in US, that is unique, and in a company or in even IIT, if you take, each person has an employee number, employee identity, that is unique. No two person will have the same employee number. So, you can store according to that employee number, which is serves as the key, and you store the records and you have to search through the key, and you may use ternary trees or binary trees. First, let me see how you can store records using binary trees. For simplicity, let us consider only some integers, how we can, let us take only integers. There are two ways of storing the records. As an example, you have this. Number, say 7, 5, 3, 10, 8, each record is stored in a node of the tree. This is the tree, and each record is stored in a node, internal node or leaf. So, if I want to search whether 9 is present, how will I go about searching? First, you go to the root, all elements less than 7 will be in the left subtree, all element greater than 7 will be in the right subtree. So, suppose I want to search for 9, I go to the root, I find that 7 is less than 9. So, the next search I have to do in the right subtree. So, I go here, and here when I see 9, 9 is less than 10. So, here I have to go to the left subtree, and here I find 8, 9 is not there. So, that record is not found. Now, you can add that 9 here, 8 is stored here. So, if you want to add 9, you have to add like this, 9 is greater than 8. So, it has to go to the right subtree of this. But then there will be some balancing also done. See, next one, if you add, suppose I want to add 14, I will add like this, then 16 I have to add like this. The height of the tree will keep on increasing. So, there some balancing also will be done, that will be explained in the data structures course. You will learn about that in the data structures course. The main idea is tree as a structure, how it is used. So, you can store the record in each of the nodes, and you can search like this. Each node will contain the key value, and if you are going to search for a value which is less than that, you have to go to the left subtree. All the nodes on the left subtree will have values less than that, and all the nodes on the right subtree will have values greater than that. This is the way data are stored. Another way of storing is you store the records only at the leaves, and in the internal nodes you store discriminating values. They are called discriminators. The records are stored only at the root. Let us see how this is done. Take this. The leaves store the values. The same values we can take 3, 5, 7, then 9, 12. The values are stored like this. The root will contain a discriminator. It could be something like 8. Now, all values greater than or equal to 8 will be stored on the right subtree. They are stored at the leaves. All values greater than or equal to 8 are stored in the right subtree. Now, in this node, you must have a discriminator which tells you what are the things which should go to this. Something like, say, you can have 12 here. All values greater than or equal to 12 will go to this subtree. And here you can have something like 13. So, the value 12 is on this side. If the value is 13 or more, it will be on the right subtree. And here you can have a value like, say, some 10. This is a discriminator. All values less than 10 will be going to the left subtree. Greater than or equal to will go to the right subtree. There is no right subtree here. If you have a like record, say 11, it will go here. 10 or 11, it will go here. And similarly, in this tree, the left, this value is 3, 4, 3, 5. So, you can have a discriminator 4 here. All values greater than or equal to 4 will go to the right subtree. All values less than 4 go to the left subtree. And here you can have something like 6. So, all values less than 6 go to this subtree. All values greater than or equal to 6 go to the right subtree. But in this case, the values are stored only at the leaves, and the internal nodes contain the discriminators. This is one way of doing. So, there are two ways of storing the records, and we have seen how to do that with binary trees. Let us consider ternary trees, where the values are stored at the internal, not at the internal nodes, but only at the leaves. These ternary trees are also frequently used. Each node can have 2 or 3 sons. So, here we can have 3, it can have 2 sons or 3 sons. Now, again this can have, say, this has 3 sons and this has 2 sons. This you can take as a leaf, say, for example. And this may have leaves. like this. This may have say 3 sons like this. This has got 1 son and 2 sons. Some records you store here. Let us see how they are stored. 2, 4, 7, 10, 12, 15, 20, 21. And here 25, 30, 32, 37, something like that say. Now, when you have 3 sons, this node will have 2 discriminators. The first one here in this case it can be something like 21, all values which are equal to 21 and the next value x say less than x will go to the middle subtree. Here from 25 we are having, so I can have something like 23. So, all values which are less than 21 will go to the left subtree, which are equal to 21 and greater than 21 but less than 23 will go here, which are greater than or equal to 23 will go to the right subtree, the third tree. And if a node has just 2 sons, as in this case, there will be only one discriminator here. So, the least is 31, you get 32 and 37 you have. So, one value can be 31, all values less than 31 will go here, all values greater than or equal to 31 will go to this subtree. Now, here you are having 25 and 30. Maybe I should draw it in a slightly different way, so that the left and the right are clearly seen. So, here I should have a value such that it should be more than 25 and less than or equal to 30, something like 27 I can have. So, that the lesser value goes to the left subtree and the right greater than or equal to value goes to the right subtree. Here also we can have, there are only 2 sons, so I can have a value say something like 35 here. So, that values less than 35 go here to the left subtree, values greater than or equal to 35 go to the right subtree. Now, this has got 3 sons, so there should be 2 discriminating values here, and the values, the middle subtree contains 7 and 10. So, I can have something like 6 here. So, all values greater than or equal to 6, but less than say 12 go to this subtree, and all values greater than or equal to 12 go to the right subtree. Now, look at this, this again has got 3 sons. So, here there should be 2 discriminating values. I can have something like 14 and 17. All values less than 14 will go to the first tree. All values greater than or equal to 14 but less than 17 will go to the middle subtree. Greater than or equal to 17 will go to the right subtree. So, the discriminating values we have to choose something like this. Here there are only 2 sons, so I can choose a discriminating value like this, and here there are only 2 sons, I can choose a discriminating value like this. So, the internal nodes only contain the discriminating values. If it has got 3 sons, it will have 2 discriminating values, and if it has got 2 sons, it will have only 1 discriminating value. So, these ternary trees, sometimes they are called 2-3 trees, and this type of a tree is called a 2-3 tree. Each node can have 2 or 3 sons, and it is somewhat this is not balanced, but all the leaves, in some cases you expect all the leaves to be at the same level. In that case it is called a balanced tree. So, in general you would like to have balanced trees, and the data will be stored at the leaves, and the internal nodes will have discriminating values. This is the main use of trees as a data structure. Next, let us consider binary trees, and the way you can search through the traversal, you can say traversal method. Suppose I have a tree like this. Have a tree like this, where the nodes are denoted as A, B, C, D, E, F, G, H, say. There are 3 methods in which you can traverse the nodes. One is called the pre-order traversal, another is called the in-order traversal, and third is called the post-order traversal. In the pre-order traversal, process the root R of the T, then if the left subtree exists, then process T1 in pre-order, and if T2 exists, then process T2 in pre-order. T1 is the left subtree, and T2 is the right subtree. So, this is the tree you are having with node labels A, B, C, D, E, F, G, H. And if you want to traverse the tree in the pre-order, in what order you will search? The root first, then the left subtree, then the right subtree. So, let us see how the nodes are traversed in the pre-order manner in this tree. So, node A will be visited first, then these 4 nodes will be visited, then these 3 nodes, and in these 4 nodes also you should follow the pre-order method, the root first, the left subtree and the right subtree. So, B will be visited first, then the left subtree is just D, then the right subtree E and G have to be visited, and here again you have to follow the pre-order traversal method, the root first, left subtree and the right subtree, there is no right subtree here. So, E and G. Similarly, the right subtree also should be visited in the pre-order manner, the root, there is no left subtree, then the right subtree. So, C, no left subtree and the right subtree. The right subtree again should be visited in the pre-order manner, root first, left subtree and the right subtree, it is F and H. So, the nodes will be visited in this order in the pre-order traversal. Let us see how the nodes will be visited in the in-order traversal. In the in-order traversal, first the left subtree is visited, and that is also visited in the in-order manner. If T1 exists, then process T1 in order, then process the root, then the third one is if T2 exists, then process T2 in order. So, in the in-order traversal, left subtree first, then root, right subtree. So, if you want to traverse this particular tree in the in-order method, in what order will the nodes be visited? first the left subtree, then the root, then the right subtree. And the left subtree itself should be visited in the in-order manner. First left subtree, then root, then right subtree. That is D first, then B next, then these two. And these two again should be visited in the in-order manner, left subtree, root, right subtree. So, G and E will be visited in that order. Now, look at the right subtree. This also has to be visited in the in-order method, that is left subtree, root, right subtree. There is no left subtree, so C will be visited next, then the right subtree. And this right subtree again has to be visited in the in-order manner. So, H first, then F, then if there is something in the right subtree, there is no right subtree here. So, it will be H and F. So, the nodes will be visited in this order in the in-order traversal method. There is one more method called the post-order method. In the post-order method, the left subtree will be visited first, then the right subtree, then the root. So, in the post-order method, if T1 exists, then process T1 in post-order, then if T2 exists, then process T2 in post-order, third process the root node R of the T. So, take the same example, and if you want to traverse using post-order traversal, in what order the nodes will be visited? First the left subtree, then the right subtree, then the root. So, A will come at the end. The left subtree itself, if you take first the left subtree, then the right subtree, then the root. So, D, then the right subtree, that again will be visited in the post order method. So, G, if there is something here, then E, there is nothing here. So, it will be G and E, then B. So, in this subtree, the nodes will be visited in this order D, G, E, B, and next the right subtree has to be visited. That also has to be done in the post order method. That is, for this one, there is no left subtree, right subtree has to be visited first, then the root. So, C will come here, and this one again it has to be visited in the post order method, left subtree, right subtree, root. So, there is no right subtree. So, H, F. So, the nodes will be visited in this order. So, for binary trees, you talk about these three methods of traversal: in order, pre-order and post order. Now, if you have the sequence of nodes visited in an in order method and a pre-order method, from these sequences you can construct the tree. Similarly, if you have the sequences corresponding to in order and post order, you can construct the tree in a unique manner. But if you have the sequence corresponding to pre-order and post order, you cannot construct the tree in a unique manner. For example, I have 4 nodes like this, say A, B, C, D. The in order will be, pre-order will be, here will be A, B, C, D. In order will be B, A, D, C. From this you can construct the tree in a unique manner. How can you do that? Suppose I do not have this, I do not have this. How can you construct the tree? The pre-order A is the first, so A is the root. In the in order, A is the root, so whatever is appearing on this side is the left subtree and this on the right subtree. So, B is on the left subtree, there is only one node, so it has to be like this. On the right subtree you have C and D, and C and D have to be the right subtree, The first one will be the root of the right subtree. So, C will be here, and where will be D? D can be here or here, right, but this tells you that in the inorder left subtree first, then root, then right subtree. That means D has to be the left son here. So, you can draw like this. So, from pre-order and in-order you can draw the tree in a unique manner, but you cannot do that if you have pre-order and post-order. For example, if you have something like this, A, B, C, D, what is the pre-order? The pre-order is A, B, C, D, the post-order is D, C, B, A. From, if you are given this, the tree can be like this or it can be like this also, A, B, C, D. What is the pre-order for this? A, B, C, D, post order is D, C, B, A. So, the tree can be this or this. So, from these two sequences you cannot construct the tree uniquely, whereas if you are given in order or pre-order, in order and pre-order or in order and post order, you can construct the tree in a unique manner. And if you look at expressions, arithmetic expressions, the use of it will be very clear. Now, we can see how these traversal methods are useful when you look at the trees as arithmetic, representing arithmetic expressions. We can also see some of the other concepts about trees like spanning trees, weighted spanning trees, etc. in the next lecture.